Good evening, everyone, and welcome to the Vacuum Transport Seminar. We're very happy to welcome you tonight for two interesting talks, both organized by the EuroTube site. And I will head over to Daniel from EuroTube in a second to give a short introduction of the speakers. Just as a short information again for the audience, we use this tool called slido.com to pose all the questions during the seminar. And we invite you to go to the website and enter the code. The entry code is VAC Transport Seminar. And then during the presentations, you can pose all the questions. And then after every presentation, we go in detail through the questions. So I see Lucas is just putting the details into our chat of this conversation. Yes, so I would like to hand over to Daniel to give a short introduction of the first speaker, and then we wish everyone fun with the presentations. Thank you very much.
Thank you, Natalie. Also from my side, hello everyone, and welcome to the seminars once again. Today we have the pleasure to welcome Dr. Joseph Sogming La, who is Vice President, Head of Corporate Strategy Department at Posco Europe. And based on his past experience, we are having today a person who is very experienced in not only civil engineer, but in the construction side overall. Today we will be having a talk about new steels and tube designs for the future, more with regards to the Hyperloop industry. So I'm very much looking forward to more to these insights, Joseph, and I give you the floor then for the presentation.
All right, thank you, Daniel. As introduced, my name is Joseph La. I am here positioned in Posco Europe, which is in Frankfurt, Germany. And my presentation will be about our past experience and activities within Posco on Hyperloop. So let me start. Just a short, very glimpse of for Posco for the people who does not know us. Well, Posco is a steel making company. We were established in 1968, and from there we grew. Currently, we have about 196 of subsidiaries or affiliates within the Posco Group, with the companies such as Construction E&C, Posco Chemical, ICT, our IT company, also Posco International, our trading company, and research institutes. There are 33 domestic and 163 overseas. For Posco, we get our name from where we started, at the city of Pohang, as you can see in the picture right there on the right bottom side of Korea. That's Pohang Steel Company, so that's where Posco comes from. Now we have two mills in Korea. The first one in Pohang, the second largest integrated mill in the world with about 17 million tons. And the secondary mill in Gwangyang Works. That will be the largest integrated mill in the world with a capacity of 21 million tons. So within Korea, we have 38 million tons of production capacity. Globally, we have 41, 42, some-ish. That makes us about 6 in the world for quantity wise. But on the right, you can see we have been the world's most competitive steelmaker for 12 consecutive years since 2010. Our revenue is somewhere around $68 billion and so on. So just a short glimpse of where we come from. And then to my next slide. This slide was not shared in the Hyperloop conference before. The rest are mainly from the Hyperloop conference presentation. But this is where how our interest in Hyperloop started. There was a paper back in 2009, I think it was from university in Austria, that had this concept of a vacuum tube and transport. So for passenger, I think it was targeted more on passenger. But when we found that paper and then read it, we thought it was very interesting. So what we did was we launched a feasibility study in 2010, which lasted for 2 years. And I think many of you already know that it was 2012 or 13 that Elon Musk came up with the word Hyperloop, but our interest started before. So what we did was to see how this could be feasible. So in a tube, which is on a vacuum, which would reduce the resistance for the trains to follow. Now, all our feasibility results showed to the fact, and also we looked into several lines that we could actually construct this type of Hyperloop within Korea. And the result came to a conclusion where unless the technology had a switching technology along with it, it would not have the economical feasibility. So what came out from our concept was a low speed, semi-vacuum tube, of course, autonomous, with a freight size according to the pallets, and then, of course, different kind of details within the structures. The reason why we came to a very low speed was that unless with the loading and unloading issues, it would be meaningless to send it to 1,000 kilometers and then have it to wait 1 hour or 2 at the end to load and unload. So this is where we started. And then after our 2 years of feasibility study, we stacked it and waited until the technology actually came out that we thought this could come more commercialized. Then what happened was that in, I think, 2019, we saw a Hyperloop company in Europe, of course, HART. They launched their 30-meter test tube, which showed they can do the switching technology. Then we got interested and took our previous interest back on the table, and then we approached Tata Steel, and then asked them, because it was in Netherlands that we approached Tata, and then asked if they would be interested in working together to assist in the Hyperloop development. So Tata Steel and Posco have agreed, and then we approached HART and then started to have this joint collaboration to support the Hyperloop industry. Now, what happened was when you talk to of course, I do have a civil engineering background, but when you talk to an engineer, engineers usually talk from the structural side. So we talk about this stiffness. But when you talk about, when you come from the material side, such as steel makers, we come from the material language, which is mostly strength. So although we talk the same language, there is a different meaning or a different approach of where we come from. So what we did was we talked to the HART engineers and asked them, what are the actual items or features that you are looking for from the steel side? So from there, they came up with several issues during operation, during assembly, and then during maintenance or operations. And then we had a long workshops and discussions, and then came up that let's do, instead of using a typical steel for Hyperloop, let's come with something that could better support the needs of the engineers, and came up with 3 items. So long-term durability, machinability, and weldability was the 3 items that we took on for our joint R&D. And then from those 3 topics, if we come back into the steel side, it goes down to where damping property was chosen, and then yield ratio also for a better easy machinability, and then improving CEQs for the weldability. So considering the different chemical compositions, heat treatments, or the microstructures, new steel grade was developed with improved damping performance and lower yield ratio and similar weldability. So if we go into the details a little bit more, improving safety was an issue from two sides. So one was damping. So currently, compared to the regular S355s, the new steel grade has about 1.6 to 2 times better in damping ratio. And also along with that, we wanted to add the low temperature toughness. So that strength is about 4.7 times compared to the regular S355s. Meaning, if you look into the actual performance or what happens in the Hyperloop tubes is that you see a lot of vibrations, and then that will lead to fatigue, meaning better damping will actually help in the safety issues. And also Hyperloop, wherever it is around the world, it will go to a region where there will be very low temperature. So that also will improve the safety issues. And then came the second issue was that there's going to be a lot of welding, drilling, cutting, a lot of machinability. Meaning to assist that, it would be good to have a better yield ratio. So yields, and we looked into the actual structural part. Do we need to go higher in strength, or do we need to have a better yield ratio? And then we found out that usually the loads into a Hyperloop is currently not requiring higher strength. So then meant that we should go to a better yield ratio. Lowering yield ratio means that it would have better formability. You'll be better and you'll be able to do a lot of manufacturing or other process with it. So about 10% was improved accordingly. And for last one, easy weldability, we were able to do a little bit more slightly, but about 5% improvement in the weldability. But then the issue came out, do we really want to take it that low? Because other products that will be welded to the pipes will be existing pipe structure materials. So then we said, okay, let's leave it as it is. Although it has better performance, our criteria will stay the same so that it would have a same or more compatibility to other the current materials that's in the market. Of course, in order to support the weldability, we need to be able to share other solutions along the welding process. So, and therefore, the first Hyperloop steel grade just for Hyperloop was developed and implemented. Now, when you do these kind of developments, we do not do it by ourselves. We know that just developing the steel grade and leaving to the market to use it does not really work. And I think my colleague here wanted me to share the actual sample, if you can see it. That's the actual sample of the steel grade. It was manufactured according to the actual thicknesses that was done. The actual material has been produced and also made into pipes and is now being assembled with the other supports and the tracks currently at a facility in Netherlands. So what happened was that let me give you a glimpse of what this kind of new steel development actually means. It means in about, I think in money-wise or investment-wise, about several $1 million, because we would have to actually do it in our small labs and then go into pilot plant productions and then go into our first real facility to do the actual manufacturing, which at a steel mill will be somewhere, not just, we cannot produce 1 ton. We're making, when we're doing the actual production on on our facility, it goes into hundreds of tons. So several tests have been done. Also, all have been tested in our laboratory to check their mechanical and composition-wise testings. And then when we were satisfied or comfortable to launch it, we worked with a pipe manufacturer and then did the pipe manufacturing. So all the pipe manufacturing process for the spiral has been done. And then from there, also test samples were cut off and then mechanically tested also. And then do that again to see if we can do a lot better. So several pipe manufacturings have been done, but trial and errors or repeatable tests so that we can improve it a little bit more has also been done. Along with that, when we do the welding, when we touch the welding issue, we need to have share the welding consumables and also the welding procedures. Those WPS has been also been done with all the related electrical parameters. So the pipe has been made and has been delivered to the manufacturer right now. Now, what's next? We believe that there can be more that steelmaker can support in the Hyperloop development. Of course, there is a lot of arguments or reviews on what kind of materials other than steel that can be used in Hyperloop tubes. I know there are some projects looking into concrete, but from our side, of course, it's our business, but we believe that steel is the right material. And that was the beginning of what our journey back in 2010. With the new steel material, what we think we need to do more is touch a little bit on the structural side. So there can be different types of sections or pipes that can better support the Hyperloop. And from there, we will be doing further collaborations with different types of Hyperloop companies, and then trying to see what structural pipe section will be the best to handle or cope with the Hyperloop requirements. So within the 20 minutes that I was given, this will be my last slide and the Hyperloop. And you can see from Tata and Posco, we have launched our brand names for the steel grade for Hyperloop, which is Postloop and Impetus. So that will be the last slide of my presentation. If you have any questions, please let me know.
Well, thank you very much for your presentation, Joseph. It was great seeing you again. I think we've all met already at the Hyperloop conference. It was great having you here as well. I've got a few questions here already in Slido, so I'll just leave them out to you for you to answer them. So the first question is, how do you currently face the challenge of increasing the welding speed? Are you looking into new welding techniques?
Our R&D was based on the current processes that is being used. So meaning our weldability, we know, of course, everyone wants to do it twice as fast, but that is for welding with the current process, it is not possible. Usually what happens when you need that, you put two lines. So spiral welding or other welding, when you make the pipes, either you do it with two different lines or two different way of doing the welding from both sides. So that is not the case. For us, if you do a simple welding as is the same process, it will be about 5 times faster. But then the issue is, it's not on our steel. It will be on the other material that's being welded to the steel pipe that you have to follow that criteria. So other than if we change everything into a new material, that we just left it that it will not be, it will be as the same as it is currently right now.
Is it the hybrid welding technique or is it laser or gas welding? What's the type of welding? No,
it's the same sub-arc welding process that is being used in the pipe manufacturing.
Okay, we've got more questions. Let's go through those. Which industries do require similar properties of the steel like Hyperloop does? So where do you see maybe benefits for other industries with the steel you have developed right now?
Well, for this steel grade, we have only targeted Hyperloop. Amazingly, that is very, may sound really awkward, but it came from a different approach. Usually what we did, what steelmakers do is that we launch our new steel grade and ask for the market to follow. So when we go into higher steel grades, let's say S690s, 960s, or even further, that will be the way how steel manufacturers go. So for example, there are 2 gigapascal steels, so 2000 megapascal steels in the market already, but that is according to the automotive industry or other specific parts. And then there are requirements, and we go further on that. But here, a unique part is that we ask the Hyperloop engineers to what they want. And from their requests or requirements, we try to match as much as we can from the steel side. So it was just developed for a Hyperloop. I hope we can find different applications, but currently we are not considering that.
Okay. Then there's a question about the feasibility study, whether that is openly available or not.
Our feasibility took 12 years ago, I think. Is that the case?
The connection of Lucas is lagging a bit. The question was more if it's openly accessible in case someone would like to have a look into it.
Of our 12 years ago feasibility study, right?
Yeah, exactly. The one in 2010. The 2010, yeah.
Unfortunately, I can't. We are not able to share. This was our private research done internally. Sorry for that. Although it is very outdated, I think.
Yeah, it's understandable.
Yeah.
Yeah, fully understandable. Then there's one more, which says it's 100% recyclable. So what else do you need besides the steel you've already processed one time? Do you need other ingredients that go into the steel, and how do you recreate this new steel? What kind of additives do you need to add to the steel?
For this new steel grade.
Yeah.
For this new steel grade, there are 2 different features that has been touched. So one will be the chemical composition, and the second will be the actual production process. Unfortunately, I cannot go into the details, but those 2 sides have been touched so that they will come to this unique criteria in the steel's final product. So there's been a lot of different approaches, testings, lab tests, and concept developments doing this. This has been almost 3 years of work.
All right. Has there been any development going into making the steel production cheaper? I would say there's probably not much to do.
No. This production has been done on our own production line already. So it's not a pilot test, that lab production. This is a full production, meaning
how can you make it cheaper? Is there a possibility? It's probably with energy demands, probably, but nothing really with materials.
With the current steel manufacturing process, I think it's more of a general question, but the cheapest way of actually going down in a special or specific grade will be have the large quantity of the order. So it is more expensive to produce small quantities, let's say for 1,000 tons, but a lot cheaper to produce 10,000 or 100,000. So on this current process, it is almost as same as the current other steel grades that has been in the market.
Yeah, so it's probably all about size. Then maybe one last question is the switches, the Hyperloop switches. Do you need a section where the track basically elongates and you have a track that is wider? How do you conquer that with regard to the structure of the tube?
Oh, well, that I think is, I leave it to the structural engineers, but from my experience, it is not a difficult issue. I can say that my involvement with Hyperloop developments for let's say hard EHC shows that that switching section, it's not hard. It can be done with the current steel grades and current pipes. The question will be, how can you be more effective? So that I think later on, when you launch the market, when you go into the market and you have the actual construction companies and the engineers get involved, they will come to a conclusion where they will design it so that it is optimized from the actual practical side.
Oh, that sounds good. So there's one more question from Alfred. Maybe he can ask the question himself because it's regarding to fire life safety. I'm not really sure what you would like to ask there, Alfred. Maybe you want to ask the question yourself. So the question would be, how do you achieve fire life safety?
Yes, that's correct. Sorry for interrupting and obviously not forwarding my question to the point. We all know steel comes with some issues when confronted with fire, high temperature fires. So as we all know, the overall system safety of our Hyperloop system will heavily depend on how we master that fire life safety. Maybe from my bottom-up perspective, this is maybe one of the top critical issues. So how do you ensure that the steel you are proposing really stays virtually physically on the safe side?
Well, if we go into the safety issue and the structural accordingly, I think fire has always been an issue that has been touched with steel. Now, this, I think on that point, is pretty much the same as a single steel bridge. So if you talk about steel bridges and how that has been designed for fire resistance, there are several methods. So meaning you can also use a paint, you can use a composite material, you can have other different types of approaches or countermeasures to cope with it. And also it will come also with the designing criteria according to how much hours or resistance that you would require. From my side, from my thoughts will be that from a safety issue, the more important will be a breach issue. So instead of fire becoming an issue, the reason why is that unless someone actually puts a very consumable material right under the pipes, let's say put a tank with their full of gas or oil and then blows it up, those kind of incidents would not be actually feasible comparable to a Hyperloop tube, but rather the issue will be the breach issue. So what happens if there is a puncture or any kind of attack on the pipe with a specific point, and then how that is developed along the tube. From our side, we think that is more critical. And that is kind of the reason why we think the steel is better material. Of course, later on, I think development or discussion will develop for the composite issues. But still, if you think about the overall vacuum conditions and how to actually maintain it, the inner shell at least, or overall, we think that will be steel.
Okay.
Interesting one. Very good question. Very good answer. Then there's one last question. I've just seen it here in the chat in Zoom. Do you have any specific calculations to understand the pot's speed dependence of resonance frequency? So with the tube, and therefore what kind of dampening and stiffness values are required? So is there some kind of interaction? What's the interaction with the tube like? That's probably on the structural engineering side, I would say. Can
you repeat the question? I didn't fully understand.
It's with regard to the specific calculations to understand the pod speed dependence on the resonance frequency of the tube, whether the tube is bending, how much it's bending, which frequency it is bending with, probably.
Oh, wow. Well, currently, I would say no. We do not have the actual, we only have the, I think, numerical analysis or such related or expectations. The actual numbers has not been really, I cannot, there's no proof or actual data accordingly with that. The only reason why there is no actual high-speed Hyperloop test track in the world. Once we have that and we see the numbers, I think that will give us more information on what we should do and how we can improve. Now, on that point, if we talk about damping and the resonance issue, the approach is not only from the material side. It also have to come with the shape. We believe that issue can be, should be touched later on with the actual shape of the pipe. That's why I think at the end, we're sharing the structural development that is necessary. But with the structures, if we can give a material that is better, it would improve even further when we go into the structural side. So there are different methods of doing it, how to conquer or countermeasure it. We'll see how the actual numbers or the requirements actually come when we actually have the high-speed tests.
Yeah, I think so too. Thank you very much for your presentation. Thank you very much for all the questions and all the answers here. Yeah, I'm very much looking forward to the shapes as well when you're looking into those. And I would hand over to Daniel now for the introduction of the next speaker.
All right, thank you.
Thank you very much, Joseph, for the very interesting talk. Now we also have the pleasure to welcome Rashdeep, so from Eurotube, who has been looking quite not recently, but in the past months, intensively on the topic on aerodynamics of Hyperloop vehicles. To be more concrete, he has been looking into numerical analysis modeling of normal shocks when they are built in the front of the vehicle, and also drag estimations when it comes to seeing how these shocks are affecting the overall performance of the vehicle under vacuum. So without further notice, Rash, I would really love to give you the word, and we're really looking forward to your talk.
Thanks, Daniel, and thank you for giving me the opportunity to give a presentation here. So let me start my slides first. Can you see my slides? Can you see my slides?
Yes. Yes.
Okay. Thank you. So my talk is about numerical and analytical estimation of the shock front developed in front of the vehicle, and what extent we can use simple numerical and analytical tools to understand the behavior of the shock and also predict something about the drag estimation of the vehicle. So basically, my talk is about this viewpoint. So in Eurotube Foundation, we are working on aerodynamic studies regarding vehicle movement inside such closed tube system, and we developed some kind of simple tools to understand it. One of them is, as I'm going to talk about, it's a little bit a one-dimensional piston problem, where analytical modeling can be used to understand this flow feature behavior, and also we have some numerical solutions. And then also there is an analytical solution development on choking flow, using choking flow condition, that is for finite blockage ratio. And finally, there is some comparison of 2D CFD solution. So basically, if you look into the problem of vehicle moving inside a Hyperloop tube, it's a closed tube system, and that's a criticality in this particular problem. So there is a finite blockage ratio, of course, and typically a vehicle here, I have made a very simple approximation. The vehicle is like a piston shape and it's moving inside the tube. So now for a simple calculation, let's if you look into the problem with 100% blockage ratio, the idea is, can you get an understanding of what kind of flow features develop from this estimate, and can get an understanding of what is the maximum drag with this 100% blockage ratio. So one famous problem in this regard is this piston problem. So whenever a piston moves inside a closed tube system and it's moved at a very fast speed, there is some kind of shock front developed, and this shock propagates faster than the piston speed. And this shock also carries a high pressure in the front of the piston. And as the piston is moving away, in the back of the piston, a low pressure is also developed. So here you can see this pressure of the tube, and there is a high pressure developed. This high pressure shock front is moved ahead of the piston. And now the question is, what can you get an understanding of what is this shock strength will be? That means this ratio of this pressure, and what will be the shock speed from this solution. So for that, we need to look into the problem from the point of view of this normal shock front. Typically in the tube, if you look into the problem from the tube reference frame, the shock is moving ahead of the piston. But this kind of problem can better be understood by looking into from. So first of all, of course, if you look into the from the tube reference frame, this shock front is developing. Ahead of it, there is a pressure of the tube, and behind it, there is a pressure of the vehicle, pressure in front of the vehicle. Now, if you look into the problem from the point of view of shock reference frame, shock reference frame, there you will see that from there you can understand first of all, we can develop an understanding of shock speed. So when the shock, we look into the problem from the shock stationary frame, this upstream condition is like the fluid or the tube in which we are going into, it's like this gets the shock speed, and the behind it is the shock speed minus piston speed is developed. And there is a famous solution for that. We can understand from this thing the ratio of the upstream to downstream fluid speed and pressure ratio based on this pressure ratio. This kind of solutions can be established from just by solving mass, momentum, and energy conservation equation along this domain. Now, using that, in addition to that, there is also the relative speed on the between the upstream and downstream side, which is here basically nothing but the piston speed that can also be established. So using these two equations, we can finally find out what will be the pressure ratio, because piston speed in our case is the vehicle speed. So from that, we can understand what is the pressure ratio, and also the temperature ratio and other quantities can be established. Also in the tail end of the vehicle, because the vehicle is, or in this case, the piston is moving at some speed, there is an expansion wave develop, and this expansion wave saturates into the tube pressure at a finite distance. But it can also be established from just by solving the mass, momentum, and energy conservation equation. What is the back pressure? So a maximum back pressure and maximum front pressure can be established. From there, we can understand what is the drag calculation, and here is the solution. So basically, we can know the pressure solution, typically pressure ratio from there, and given the tube pressure, you can know the pressure solution. Typically, for example, if you look into some specific piston speed, or in our case, the vehicle speed, like about 400 at a speed of 200 meters per second of the vehicle, we get about 490 meters per second of the shock. So that means shock is moving much faster than the vehicle. As you can see, always shock is moving much faster than the vehicle. And there is also a pressure jump develop. Pressure with the pressure jump, there is also temperature, high temperature develop in the front, and there is also low temperature also develop in the tail. I will talk about it in later. From that, we can calculate the drag and the drag coefficients also, and this gives us a maximum estimate of pressure induced or shock induced drag on the vehicle, and as well drag coefficients. Now, if we this allow us, because this shock as it is propagating in front of the vehicle, one important feature we didn't consider here is the friction effect. All the friction is attenuating, but if we just try to understand what will happen to what will be the fate of this shock as it is moving ahead of the vehicle, and if there is any other blocking region in front of the vehicle a little bit far distance, because the shock is moving much faster than the vehicle, then there will be a reflection of the shock, and the shock is coming back into the system. So basically, the energy that the vehicle is provided into the fluid medium, it is actually hitting back the vehicle at some point. So therefore, it is also important to understand what will be this reflection effect, and if there is any reflection, what is the corresponding impact on the drag of the vehicle because of this. The problem can again be looked into the same thing from tube reference frame. In the tube reference frame, now we know that there is and as it is interacting with the tube end wall, there will be reflection shock developing, and we can look into the problem again from the shock stationary frame, and this time it's a reflection shock stationary frame, and we can calculate what will be the corresponding, because now we know the pressure in the front of the tube, in the behind this shock, because of we calculated previously from the incident shock wave. Now from the reflection shock wave, we can know what is the corresponding tube pressure developing now in this case. And this can be calculated again using the same features of upstream to downstream pressure ratio, and finally we can estimate what is the reflection pressure ratio. So this is an important point, because as we look into the problem, for example, if a vehicle is moving ahead from quite a far distance, and this shock attenuation is not enough, then this shock is moving ahead of the vehicle, hitting the end tunnel and coming back to hit the vehicle. Here you can see this multiple reflection effect on the vehicle. So vehicle is moving ahead, shock moves ahead and then comes back to hit the vehicle. At some point, it leads to a jump on the vehicle drag, and this is therefore there is a potential thing to be worried about, which is about how this what is this instantaneous jump in the drag, and what is its corresponding influence on the vehicle safety or vehicle stability issue. And we can see that there's a continuous drag jump. Of course, this is a much more it's a much more extreme condition, because we are not taking into the attenuation of the shock, but therefore it also indicates us that this kind of reflection effects are there in the closed tube system. So we need to be careful with the shock reflections or shock interactions with the vehicle. Now, the thing is that in the previous solutions, we just see that analytically we can understand the shock features, but the question is, vehicle will take finite time, because vehicle is not instantaneously getting into this velocity. There is a finite time for the vehicle to get into this finite speed. That means by acceleration. So can acceleration has an effect on the shock speed or shock strength? So this kind of features now require more detailed understanding. But rather than going to very complicated CFD solutions, we can also get an estimate from one-dimensional numerical solvers. So what is one-dimensional numerical solvers is that more or less it's like that we're averaging the solution over the entire cross-section of the tube, and there we can have an estimate of mass, momentum, and energy conservation equation, averaged mass, momentum, and energy conservation equation over the cross-section. Now this kind of problems can be solved numerically again. So just I would like to give a feature of how the numerical methods we developed. So of course the domain is now can be divided into finite grid nodes, and from there we can there are certain fluid discretized nodes, and because of the vehicles present, there are some nodes which will be called ghost nodes. So when we develop the numerical methods for such kind of problem, we need to understand how we need to track basically the location of the vehicle, because there are cells which correspond to fluid flow, and there is a cells which are correspond to vehicle. This kind of problems, and then we can also convert it into a simple numerical solver. As I talked about, there is a famous numerical solver, finite volume method can always be used, and this requires a very critical understanding of how the fluxes can be calculated as in the vehicle boundaries. Sorry, not vehicle, fluid node boundaries, and then we need to get a discretized understanding of this fluxes. These solutions can be established a number of ways. It can be established because this becomes a completely hyperbolic problem, which means the waves are propagating at finite speed, and we need to understand which directions the waves are propagating. Some of the famous schemes are available here, and one of the schemes we use here is the Van Leer scheme. Using that, we can understand how what is the direction of wave propagation, and can perfectly capture the discontinuities or jump in the solution of pressures along which direction they are happening. Okay, so now like presence of vehicle makes a little bit complicated in this problem, but the thing is that if we track the vehicle's location correctly in the code, we can understand where to implement the boundary conditions corresponding to the vehicle, and we need to implement the boundary condition to satisfy certain conditions. In the case of vehicle, the vehicle wall, we should not have any mass flow rate across the wall. So that condition needs to be implemented when you implement this kind of numerical solution, which is implemented in a way that consider the wall speed, introduce a ghost cell inside the vehicle, the first ghost cell, such that the relative speed between the ghost cell and the wall of the vehicle is opposite of the relative speed between the fluid cell, next fluid cell, and the wall of the vehicle. And by that, we can implement the this mass flux, no mass flux condition in this particular problem. This problem, we are considering adiabatic condition. That means vehicle wall is not having any heat flow into the system, but it's in ideal condition. We can also go to isothermal condition where the vehicle has a finite temperature. But in that case, we need to do some special boundary condition for the energy equation. Now, with these features, we can solve the problem, the vehicle moving inside the tube. And I would like to quickly show you a video about this thing so that I understand that the power of this kind of developing numerical solutions, because we can, so in this particular feature, you'll see this particular step jump is representing the vehicle, and there's a fluid pressure. And as the vehicle is moving into the system, the fluid pressure compression wave is generated, and slowly it's converted into the shock wave. So you can see as the vehicle is moving ahead, there's a compression wave is generated, and at some point it's converted into shock wave, which interacts with the wall, and then it has a number of interactions because at some point vehicle stops. Similarly, if we have a periodic boundary condition, it is not an interacting periodic boundary condition, means like they are you can consider a circular system where the track is like a circular. In that case, the shock is moving into the domain, and it is also interacting with the vehicle later. So this shock is never going to disappear. It is always there into the system because of the closeness of the tube, but it will either interact directly by causing this kind of sudden step jump, or interact indirectly in the case of periodic system. So again, we can see that there is initially, but vehicle acceleration has a role into it. You can see initially that in this particular solution, the pressure wave is generated, but after some point, pressure wave is converted into a very thin length scale solution over which this pressure jump is happening, which is we are considering here the shock wave. So this shock wave strength is, as we have calculated, is doesn't change due to the acceleration effect because of this 100% blockage ratio condition. But of course, and also we see this kind of reflection condition that we saw here. Vehicle shock wave is reflecting back into the system. This effect is also seen numerically, but it has a finite time scale over which this full shock speed is developed based on the acceleration. Here I use quite a large values of acceleration just to have a quick solution to be developed, but we can always see that there is a time scale over which this is the time spending a time scale over which this front compression wave is completely converted into a shock wave, which is equal to the analytical solution of this particular case of 200 meters per second, about 490 meters per second shock speed, but it will take nevertheless a certain amount of time scale for this shock to develop. And also similarly, a drag also drag on the vehicle also takes some time scale to fully develop because of the acceleration effect, but the reflection effects are independent. So the thing is that acceleration can delay the process of this kind of reflection because the vehicle will take some time to convert it into shock wave, but nevertheless reflection shock wave can be developed if there is another approaching wall ahead of the vehicle. And also we can look into the time scale over which this full shock strength is developed with the acceleration effect. So this kind of numerical tool therefore help us to understand the effect of acceleration into the system. In addition to that, I don't have a solution here, but just I would like to show that that we can also have a solution, for example, for multiple vehicles into the system. For example, in this particular problem, I'm just showing that there is a multiple vehicles are present, which can be resolved also. And as you see, the drag solution is now not increasing, but there is a jump or there is a fluctuation on the drag because of interaction between the two vehicles with time. And this effect is persistent and present. We have to do further analysis to take into consideration the friction effect into this problem, but we can always see this kind of fluctuation that has developed because of multiple vehicles present. Okay, so now we have been able to understand the shock, this normal shock from developing with the 100% blockage ratio. But what is the finite blockage ratio? How we can predict the value of the shock strength because of the finite blockage ratio? And here is also an interesting observation that vehicle can be seen as equivalent to a choking nozzle. So what happened in the choking nozzle is that in a nozzle, which is a subsonic nozzle. So when in the upstream side of it, if the flow has subsonic features, and as the nozzle area is decreasing, it accelerates, but it can accelerate only to the effect that at the throat of the nozzle, a Mach number 1 condition develops. And if we try to push the fluid at more fluid through this system, there is a shockwave developed in the back here to change the upstream condition. So vehicle also behave like similar to that in this case, because vehicle also suddenly changes the available area around it for the fluid to flow. So therefore, there is also possibility of choking condition to develop, and that always develop at any finite blockage ratio at higher speed, and the flow will become sonic at some point, and then because of this decreasing vehicle area, it will be behaving like a Laval nozzle condition, and the supersonic conditions can also develop in the tail end of the vehicle. But can we predict the upstream shock conditions by using this choking nozzle? And the answer is yes, we can, to an extent. That choking in the choking nozzle case, first of all, we can understand what is the Mach number that correspond to this choking nozzle condition in the upstream, and from there we can calculate what will be the corresponding blockage ratio. But now the question is, if we know the blockage ratio and the upstream condition, we can always develop a solution for shock to propagate in the upstream. That means this time again, if we are standing on the, we are considering this, we know the downstream Mach number, we know the upstream condition completely, and we know that there is a shock is propagating. So across the shock, what will be the behavior? That can be understood by, again, looking into the problem from the shock stationary frame, move with the shock, and a solution can be developed from the mass, momentum, and energy conservation equation. We develop this kind of solution, and we see what are the pressure ratios, what is the shock speed, what is the temperature on the ahead of the vehicle. And the question is, this 1D calculations, can we trust into it? Means can we have an experimental tool to see that really this kind of features are developed? Well, currently we do not have a Hyperloop running, so we cannot do the experimental analysis, but we can always do some more detailed CFD calculation. And that's what we did it here. We try to see if by 2D CFD solution we also get this kind of shock features. And yes, we see this shock features if it's all implicit compressible flow solution in the 2D, that a shock front is developing ahead of the vehicle, and because of this because of the supersonic nature, there is an oblique shock is developing in the tail end of the vehicle also. And now from this solution, as if we solve it in a transient mode, we can understand how the shock is propagating. Initially, because of the vehicle curvature effect, there is also curvature in the shock, but later this normal shock completely develops. And this shock with defined vehicle speed, the shock speed is with the increasing vehicle speed, relative speed between the shock and vehicle is lower. It is to be understood that absolute speed of the shock is still higher, because shock is we have to add here the vehicle speed on the shock in this particular kind of simulation. And we can establish how this pressure jump is propagating forward. We can calculate the shock front, that is what is the speed at which this pressure jump is propagating. Interestingly, 1D analytical and 2D numeric matches decently. At higher speed, we get a little bit difference in the shock speed calculation, but this pressure jump, which is very important, we get a good understanding, good match there. And also from the 2D, you can see this lower pressure developing the tail. So there is also an essential feature that this how to control this low pressure development. That means this oblique shock development, which can, in the case of viscosity induced problem, there is also possibility of shock boundary layer interactions, which can further reduce the pressure and therefore increase the drag. these calculations we have we have done, but I'm not showing it here currently. But there should be some control features developed in the tail end of the vehicle to understand to reduce this kind of drag that our analysis shows. Finally, again, I'm not going to the details. Just 1D numerics, similar to 1D analytics, 1D numerics can be done also for the finite blockage ratio case. And from there also, we can understand what will be the shock speed developing. It will reduce definitely the time scale in which computational time scale for the shock solution, and we can also capture more complicated phenomena like acceleration effect. But here, how to solve this thing? We have to similarly do this area average solution, and this time we have to take care of this area averaging of this mass, momentum, and energy conservation equation. From there, we have established some solution for the pressure and temperature. It requires a little bit more understanding to see like how much well match you can see with 2D numerics and 2D analytics. Currently, this is the feature that we are seeing that it is a little bit under predicting compared to the analytical solution, but it's interesting to look into further details here. So finally, as a conclusion, I would like to say that piston analogy is very useful to understand what is the maximum values of pressure drag and shock strength, etc. And it also provides an understanding that there is a shock reflection possible. Vehicle acceleration delays the full shock speed development, but shock strength still remains same. And shock speed of the finite blockage ratios can be predicted using this kind of choking nozzle analogy. And area averaged equations can also be used to understand these important flow features, both in the front and the tail end of the vehicle. Further research objectives based on this kind of research, so far the research that we did is that we understand an interesting feature, which is the shock development at high speed. And therefore, definitely there is a requirement to control or reduce the shock strength by a defined attenuation mechanism. Also, there is another important point that there's a reflection shock is considering a sudden jump in the drag. So there should be measures to control this kind of drag jump by instantaneous shock vehicle interactions. And other Hyperloop studies, for example, thermal effect is also required look, because there is a high temperature develop in the front and low temperature develop in the back. So can we do some other measures to understand how to deal with this kind of high temperature effect on the vehicle? So with this, I'd like to conclude my talk, and I'd be happy to take up any questions if you may.
Well, thank you very, very much for your presentation. There was a lot in there, and I was barely caught up to most of it. Well, thank you very much. I've heard some of the Laval model stuff already talked about for Hyperloop, so it's great to see you catch up on that as well. There's a few questions on Slido that I would like to ask you. So the first one is, do these analytical solutions also present a model for the 3D world? Is there a possibility to 3D model it, and how do the analytical solutions relate to the 3D flow?
So analytical solutions are limited here. Like and they cannot perfectly capture the 3D effect, because 3D effect also have this kind of like a lift effect is also there, another solution. But it can give an understanding of this shock speed and the shock strength kind of problem. So basically, in the front of the vehicle, there is some high pressure developed that we understand. But this high pressure front is moving forward. So basically, what 1D or analytical solution is giving us, that we will understand when we develop, if you want to calculate the solution using this 3D full 3D CFD methods, what kind of maximum domain size we need, or what kind of transient solutions we need to develop in order to capture all those effects. It will give a maximum estimate, but so far it is not enough. Of course, in 3D we need to go a little bit more detail. Of course, we will see more detailed effect in 3D.
Well, I'd love to see the experiments after that. About that.
Yeah.
The second question is, what happens with the shock wave traveling faster than the pod with regard to two pods behind each other? But I think you had that in one of the slides where the pressure oscillated between the pods.
Yeah. So here it's an interesting phenomena that the shock speed moving from the tail end of the vehicle is interacting with the front end vehicle, and expansion of coming back from the front end vehicle, and this kind of in this setup, because an interesting point, we did not consider the friction effect on this thing. So there it will gonna dissipate. But for the timing, it's also have a time scale over which it will oscillate. So that oscillation we have captured here. But next step for us also to introduce this friction effect and see how long it will take to dissipate this kind of shock-induced drag jump on each vehicle.
And there was one question about the shock strength with regard to blockage ratio. So what is there a dependency between shock strength and blockage ratio? I think you had the shock strength on one of your slides. So does that depend on the blockage ratio, and what would it be?
Yeah, so definitely. So there is an effect. Let me show you. Okay, where is one? Yeah, yeah. Yeah. So from the blockage ratio, we can calculate, like from analytical blockage ratio can give us an estimate of what is this shock strength. That means the pressure ratio across the shock. So definitely, and is interestingly, as I'm going towards the blockage ratio one, the 100% blockage ratio, it matches that 100% blockage ratio values also. So typically, for example, blockage ratio 0.6, 200 meter per second speed, I can see about 1.6 order jump in the pressure. So that means if tube pressure is 5,000 Pascal, it can go up to 7,000 to 8,000 Pascal, the pressure jump across the shock. So definitely it can capture the value of the shock pressure jump across the shock from the blockage ratio by this analytical solution.
Well, thank you very much. The next one is about the piston and having a flat head. Well, the piston compared to a vehicle that just probably have a curved shape in front of the vehicle. And how does that relate to those simulations? And maybe you can touch a little bit on the front and the back side, because I think there have been some interesting parts about back or front shape of the vehicle with regard to aerodynamics, what you have to do.
Yeah, exactly. So this is another interesting problem. So currently, because in this problem, I wanted to see the shock features can be captured or not. That's why initially, when you do this kind of 2D simulations, we'll see a curved shock develop in the front of it, and it will take after some time. It will take some time for this shock to propagate and become a fully normal shock. And I was looking into this normal shock speed, that how it's so it will take some time to develop into this fully normal shock, and then it move ahead. So but definitely this curved shape has an impact initially, initial transient mode, how the shock develop. But later features are that what we have seen, that analytically it matches, it's kind of independent of this curvature behavior. After some time, when this fully normal shock is developed, its features are more or less independent of this. But we have done another interesting thing, that is I would like to show. Yeah, exactly. 1D numerical solver with finite blockage issue. So here, as we have looked into it, so we have considered the area average solution here around the vehicle. So here the vehicle shape effect is considered to some extent, although I didn't put the simulation result here, but we can get, like, this curvature, how long this curvature will take to develop into this vehicle like a straight, and this effect and what this effect has on the drag, we can understand from it. But currently I don't have a solution, but from this kind of numerical solution, we can also have an estimate from for this value, the vehicle shape effect. But it is not as detailed as 3D calculation, but it can give you what is the change it will give, drag change it will give because of the shape.
Great, thank you. Somebody has asked, I've seen a paper in the background of your computer, whether that's your paper and whether there's something that you've published so that they can read through it and catch up on all those information.
Yeah, exactly. So this was that particularly shock-prone development and normal shock propagation speed. We have written a paper and we have submitted in the Journal of Aerospace Science and Technology. We have submitted it. It's under review. When it's published, if it is published, hopefully, then we'll share it in maybe in this channel, or we'll inform here in the LinkedIn. Yeah, definitely.
That sounds good. Yeah, maybe we can add it in the YouTube description there as well. That's great.
Yeah.
And then there's one last question I'm seeing here. Why was the mass flow inlet boundary condition considered and not the far field match inlet boundary condition? Mach inlet, sorry. So the mass flow inlet boundary condition versus the far field Mach inlet boundary condition.
Yeah, so here, because here we have used a finite distance for the vehicle, and of course, because of computational limit, we cannot use a long distance. So in the vehicle tail or in the behind the vehicle, we consider a longer distance. In the front of the vehicle, we consider a shorter distance. And when you consider a shorter distance in front of the vehicle, and because it's become the problem is because of a shock and all, problem will have transsonic behavior. So it is always better to use a mass flow inlet condition rather than velocity inlet conditions actually in that case. But on the tail end of the vehicle, far field distance, we consider the like a free stream pressure conditions there.
Well, thank you very much for answering all those questions. I'll just head over to Natalie for the last words for the seminar and the next interaction. Thank you very much, Reggie.
Thanks for the opportunity.
Thank you very much to both presenters for the interesting talks. I would just quickly like to give an outlook for the next seminar, which is already the last seminar of this edition. And so the next seminar takes place in 1 week, again at the same time on Monday. And we will have 2 talks again. One talk will be by Nevomo and the second talk by CMOT. So we're hopefully, we hope we can welcome you again, all of you, to the last seminar edition of this semester. And yes, we would be happy to welcome you. And until then, we wish you a nice week. And in the name of all the organizers, thank you for participating and see you soon. Thank you very much.
Thank you very much. Bye.
Thank you very much. See you next week.
See you all.